Hello and welcome to today's webinar, Powering New Space Missions, Navigating the Cost versus Reliability Challenge. I'm Tom Freeman, Product Manager at Solster, distributor in the UK for VPT. And joining me for this webinar is Jeremy Farrell from VPT.
Yeah, thanks, Tom. Thanks for having us. And thank you all for joining. My name is Jeremy Farrell. I'm Director of Engineering here at VPT. I've been with VPT for about 22 years now. During that time, I've developed or I've designed or been in charge of the development for many new products, military, aerospace, several different space applications, from geosynchronous, deep space missions to LEO missions. And that's kind of what we're going to talk about a little bit today, some of the new products that VPT has to offer.
Thank you very much. So VPT is an industry-leading manufacturer of space-grade DC-DC converters with experience of flight systems for more than 30 years. Details for who to contact in your country can be found in the contact area of the VPT website. You'll find an extensive network of technically knowledgeable distributors to provide support in more than 30 countries around the world. So VPT distributors around Europe. We have AVE, Added Value Electronics, in Luxembourg, the Netherlands, and Belgium. Expando AB in Sweden, Denmark, Norway, and Finland. Incomtech in the Ukraine. Melexia in France and Italy. Protec in Switzerland, Austria, and Germany. Semicon in Poland. Solster in Ireland and the United Kingdom. And Venco Electronics in Portugal and Spain. If you have any questions, please hold them until the Q&A session at the end of the program, or you can submit them via the on-screen Ask a Question box, and we'll address as many as possible at the end. Also note that there are a live audience here today, so if you can please hold your questions as well to the end, and we'll address those as and when we can at the end of the program. A PDF of today's slides will be available for download under the Events Resources. So to start, the changing landscape in space. It's just under 70 years since the first human-made satellite was launched in 1957, and we have just gone past the 60-year anniversary of the very first commercial satellite, Intelsat-1. At the turn of the millennium, there were roughly 750 active satellites in orbit. In 2010, there were just over 1,000, so a 30% increase in 10 years. In 2020, there are approximately 3,400 satellites, so a 340% increase in 10 years. In 2024, we're already in excess of 10,000 active satellites. And by the end of this decade, we may well be over 40,000 active satellite systems. So it's not just that the number of satellites is increasing, but the rate that the number of satellites is increasing. So this huge growth in satellite and space systems is dominated by low Earth orbit satellite systems, constituting roughly 93% of all active satellites. So a more developed understanding of this LEO environment and an increased commercial pressure for high volume, low cost, and shorter lifetime missions has seen a reevaluation of what is actually necessary at a component level for these systems, resulting in a new approach to satellite design, which is cost performance optimized and generally placed under the category of new space. Jeremy, why should we listen to VPT regarding new space?
That's a great question. So VPT has been in business for about 30 years. We have an extensive product line, a lot of in space. We have traditionally, most of our space market is thick film hybrids, and we've had thousands of missions that are very successful throughout that time. VPT, we concentrate on high reliability. That is our market. We don't make super high volume parts for automotive or for cell phones. We only look in the high reliability market. So we have a lot of history. We have a lot of testing knowledge. We have a lot of manufacturing knowledge, in all these different areas. And we're also a subsidiary of a larger company called HEICO. Okay, and that has allowed us to make investments and by other companies, one of which that we're going to talk about some today is VPT Rad, which is a radiation test company. So, this new line that we're going to talk about today for LEO applications or shorter mission applications is really just an extension of the larger product line that we have. That's more just we're trying to do it at a lower cost.
Right. So traditional space power systems were kind of rad hard, hermetically sealed, thick film hybrids. Why are those not ideal for new space applications? How is VPT addressing this changed market that's new space?
So one of the things we did was we looked at screening. Typically, when you think of a space application for our hybrids, we think of Class K screening, space level screening, and it's pretty extensive. Just to look at the components that we buy, on average, we're seeing a 38-week lead time. Okay, for the components that we use to build the parts, just because of the screening of those components to put in it. So that's those components, because of that long lead time, because of that screening, they're very expensive, and then so it causes a lot of delays on when we can develop and when we can send parts to the customer. We also do an extensive amount of testing for that screening at the overall converter level also. And if you look at the amount of wire bond pull tests, every single wire bond has to be pulled. We do temperature cycling, we do constant acceleration, we do PI&D testing, we do a 320-hour burn-in, we do hermeticity, radiography, and all the visual inspections throughout the process. So all of these, each of these steps not only adds cost, it adds time. Which what we're seeing, not only for these LEO type or new space applications, it's not only cost, it's also the design development time is much, much shorter than we've seen for the deep space applications. So, we have to reduce costs, we have to reduce lead time. So what we came up with is, a different screening method, what we call ES+. So what we did is we went through and we looked at, where are we seeing failures, and, what can we do? What can we eliminate to try to get the customer a high reliability component at the shortest lead time and lowest cost? So we reduced the amount of testing that is, and so we still do temperature cycling. So we're still selling a high reliability part. We do temperature cycling. We do a burn-in. It's just less time. We still do visual inspections throughout the overall time, and all of that adds up to reduce cost, reduce lead time, but it still is not giving the customer a commercial part. It's still giving them a high reliability part that is screened.
Right. So the VIS is not it's not a hermetic product, right? And is that not important for LEO missions?
So we don't think so. The hermetic hybrid is a great technology. We've used it for many, many years. It has a lot of history, and it's great for many, many applications. It's expensive. Just to kind of give an example, the package will probably make up 50% of our BOM cost alone if we were to use that. So, so this is our solution is the VSC product line. Okay. And it's a more, what we like to call COTS, or commercial off the shelf type product. So we're using plastic parts, that we've spent, years identifying what these components are. Then we take those components and we screen them. So every lot of every component that goes into the VSC is screened. And so we look for, radiation shifts. So not every component, but every, a sample from every lot is tested for radiation. What the radiation that we test to, so the overall converter is tested up to 42 MeV. We characterize at 30 MeV for single event testing. We test for total dose 40 kilorads, and then we guarantee to 30 kilorads to give some margin. We also do elders testing. So everything is tested before we put it in, and then we fully screen it also. So you're right. This is not a hermetic part. This is what we do is it's an epoxy type packaging. So it is a very rugged structure that's designed to handle the high levels of shock and vibration that it would see during launch. And it offers still a wide temperature range, not quite as wide as the hermetic hybrids, but it does provide some other advantages like double-sided cooling. So giving it a completely enclosed structure, the customer can put the heatsink on the top, they can put the heatsink on the bottom. It gives a lot of system level design. This packaging also has been tested for low outgassing. If that's a requirement for certain applications, it's low outgassing to not cause any problems, with any kind of optics. But it still gives, very wide temperature range. It gives a wide input voltage range. We still, for our isolated products, we're offering 500 volt isolation, and they're still fixed frequency parts. Right. So, this design is using lower cost, but it still uses a lot of our topologies that we've used for years. It still uses a lot of our design techniques and circuits that we've developed over many years and very successful with.
Is screening level something more appropriate to new space like ES enough to meet this cost challenge?
So it is. It is one aspect of meeting it. The other aspect of the low cost is just using lower cost components. So we've reduced the BOM cost, we've reduced the screening cost, and we're always looking to make sure that we're reaching that optimal point of reliability versus cost. And this is a new market for a lot of people. There's a lot of new companies that are getting into this market. The launch costs are getting cheaper and cheaper. It seems like every year, and as more parts are launched, the cheaper they're going to get continuously. Yeah. So it's a lot easier for new customers to get into this market than it ever has before. Traditionally, it was really just big companies that had enough money to launch that could get into it. Now we're seeing a lot of smaller companies. So with that is creating a lot of new dynamics that we haven't seen in this market in a while, because there are a lot of various levels. Every company now has kind of a variation of their opinion of reliability versus cost. Yeah. And at VPT, we're always navigating that, and we're trying to adjust and be dynamic as possible to make sure that we're meeting all the customers' needs.
So, what does VPT have? What is a VSC, and what's in the range?
Yeah. So this is kind of for those of you that see the slides, it's a little bit of an eye chart, but it kind of gives a broad overview of what components we have released today. So we are continuously looking at expanding this market, expanding this product line. But what we have today is our isolated line is 5 watts, 15 watts, 30 watts, and 100 watts. So when we say a VSC 5, that means 5, but that's the output power. Right. It's nominally a 20 volt input bus, so that's where you're 28. And then we have a lot of different output voltages, right? So 3.3, 5, 12, 15 are kind of our standard output voltages. And that's offered both in a single and a dual output. We also have our first point of load converter.
Right.
So that is going to be
first point of load converter in the range.
Yeah,
not your first point of load converter ever.
We thank you. We do have a lot of point of load for space applications and for non-space applications.
Yeah.
This is the first one in our VSC product line, and we plan on expanding that as customer needs arise. But that's up to 50 watts of output power. It has a wide input range, up to 13.2 is the input, and it's really designed for 12 or 5 volt input, adjustable output, to meet some of the more digital demands, lower cost demands. So FPGAs, right? You can have one part for the core and another small part for I/O and things like that. We also offer EMI filters,
right?
So it's in the same packaging as our converters, still designed for low outgassing, but ruggedized structure. The way that we spec those is through the current rating.
Right.
So we say VSC F1, that's for 1 amp. So we offer a 1 amp filter, a 3 amp filter, a 10 amp filter, and a 20 amp filter.
Right.
And that's designed, those levels are kind of chosen to meet, specific number of converters, which is highlighted in their data sheets.
Yeah.
But they're designed and guaranteed to meet, conducted emissions for 461. You can see that here's just one example of 461 measurement that we've taken. All of our filters are passive,
right?
So we don't worry about radiation hardening for the filters, but we do. They are in a unique package,
right?
So that for the outgassing.
So same low outgassing epoxy.
Yeah.
Right. So they're intercompatible across the range as well. Is that right?
Mm-hmm. Yes.
So if I wanted a 5 watt and a 30 watt converter and I put them together,
yes,
no problem.
Right. You just have to make sure that you're still meeting the current requirements.
Right. So it's great you've reduced the cost, but why shouldn't I just use a commercial part or an automotive part? In principle, I could get those screened.
Mm-hmm. So automotive parts, they have a lot of testing. It's really amazing what you can get for the cost for the automotive screening. It's a lot of testing, but it's a lot of environmental testing that doesn't include radiation. They have a lot of life testing, temperature testing, and that's great. It's great really for what you get, especially for the cost. But the problem when you get out of the atmosphere is radiation. And that is the biggest challenge that we've always faced when launching anything into space, whether it's for LEO or GEO or deep space. It is all related to radiation testing. And that's what we have a lot of experience with. That's what we've done for many years, and that's what we continue to do. So this is an example of a radiation test report, or some excerpts from our radiation test report that we offer for all of our products, not just the VSC, but for all of our products. We have a radiation test report. And what you see here is just an example of single event testing and what the transients might look like. And then, how many times the transients occur, right? As you hit it with a lot of different ions, what's the probability that you're going to get, a larger transient or smaller transient? But we also characterize that for both, capacitive load or non-capacitive load. So if you look at our data sheets, we have a max capacitive load. So we test the single event transients with and without that. So if you need to reduce the transients for some reason, you can look at it with and without a capacitor to see what it looks like. So we do all of our testing for the overall converter is done once a year. So we do total dose once a year. We do single event testing once a year to make sure there's no kind of shifts. Right. But the components that we put in there are also tested on a lot by lot basis. So we do a sample from each lot of components that we put in there, and we look at that for total dose. So we will test up to 40 kilorads, for both for the overall converter and for the individual components. We do elders testing. At the design point, we do extensive amount of elders testing and look and see, any kind of shifts we have in that. We said earlier we characterize at 30 MeV We test up to 42 for any kind of latch up or destructive events. The radiation test reports, again, are available for all of our parts, including the VSC.
Right. So, you know, as if I understand you correctly, it's the screening and the radiation together. Like it's a combination of those two things, and that's the difference. So, you know, even an aerospace grade part, which goes through a very similar screening process, you know, why couldn't I use that? It's the radiation, is that right?
Yeah. So the aerospace, or will be a lot of testing, but again, we're talking mechanical, live temperature testing, and not radiation.
Right.
And that is the difference. You know, whether you're using anything that's non-radiation hardened, it takes a lot of testing that we've done over many years to develop this. And we're very fortunate to have our own radiation testing company, VPT Rad, that does this. So we can send our parts up to them. They have our full test system in-house. We can send them parts, they can test it, and we can see what any kind of shifts in performance is, almost instantly, no waiting. Single event testing, anybody that's had to schedule single event testing, it takes a huge amount of time. And, we have so many radiation hardened, radiation tolerant components that we're going, it seems like almost every month, to test parts.
Right.
So we have a very good relationship with single event test place. And then our radiation test house has their own source that we use extensively to always look and make sure that we have the right component. We make sure there's no shifts in the component over the life cycle.
So we've eliminated commercial and automotive and aerospace grade parts, but if I wanted to design my own power system, my own DC-DC, how would I build? What's the process? What's the difficulties, the challenges that I go through, that you go through?
Yeah, we've gone through a lot of difficulties over that time, and it's finding the component that you're going to get. If you go and you develop a part with radiation hardened ICs, and then you don't have to worry about it as much. The problem is you're never going to meet the cost targets. You'll be 2 orders of magnitude off in cost, and you still need to test the overall part to see what the transients are. So we've spent years developing that. I think we were a pretty early adopter in looking at this new space market and really trying to find a set of active components that'll work. Right. And there was a lot of parts that didn't. There was definitely a lot more parts that didn't work than did. So it's taking us years to build up that active component list that will work for us.
So we've gone through kind of how radiation testing has worked, and you've explained you're doing all of that in-house pretty much through VPT Rad. But what about the converter as a whole, right? It's a whole. You can't just test the components and hope that works, right? How does the whole DC-DC work?
For radiation?
For testing, yeah.
Yeah. So So we go once a year, and we look at total dose testing, and we look at single event testing, and we go and we compare that data to previous test results to make sure that we're in line, and there's no large shifts. And then we do sometimes see stuff, and we adjust as necessary.
So you mentioned Class K is just not cost effective for new space. How did you determine that? How do you determine that ES was appropriate?
So we knew that given the cost targets that we were at, that Class K type screening or level of screening was not going to be viable because we would have to pass that cost on to the customer. So we came up with ES Plus screening, but we wanted to make sure that they did have a reliable part. We want to be giving the customer the most reliable part for the price.
Right.
So we still do. So what you see here is, just a sample of a test report that our automated test system has. And, the details aren't important of what every number is, but we have an automated test system that looks at every part that we sell, and we test it 3 temp, and we go through every line of the data sheet and we run that test. We look at the results and make sure it's within the limits over the entire temperature range. And then we save all that data. We put that in a database and we do analysis on that to make sure that we're not seeing any shifts over time, to make sure that we catch a problem before it's a problem. We also do, a lot of visual screening throughout the whole process, at a sub-assembly level, at a component level, and then at an overall converter level. We still do a burn-in. So we run the part at maximum temperature for 96 hours. So we're looking for any kind of infant mortality type that will screen out components. So the Class K of 320 hours, it's too long.
Yeah.
That all adds cost and lead time to the part. So we picked 96 to try to give the customer
sufficiently low on that bell curve,
but without but reducing cost. We still do so temperature cycling, internal visual, 3 temperature testing, burn-in, and overall visual testing to make sure that it still meets all the requirements in the data sheet. And we're always open to listening to customers of what they need,
right?
And adjust as necessary. So VPT is always kind of a dynamic company that's willing to move as needed.
So you mentioned earlier that you characterized the radiation performance at 30 K-rad and 30 MeV. How did you get to those numbers? Like, where does that come from? Why is that appropriate for new space?
So, the number one is to answer the customer's needs.
Right.
We want to make sure that we're developing a part that the customer is going to buy.
Right.
So we did a lot of, the beginning, we did a lot of component screening, a lot of component testing to see what our capabilities are. Right. Then we did a lot of interaction with as many customers as we could to figure out, what their needs are, right? Making sure that we're placing the part in the right cost versus testing. So ultimately, it is up to the system engineers out there that are deciding this, what that specific company for the reliability, or the cost versus reliability curve that they're on.
Right.
Here's one example of, kind of probability of a, higher energy particle hitting the component. And we see there's a drop off around 30 MeV. So, we were at the beginning of the design cycle, we need to be kind of above that to, try to give it the most reliable part, the most probability that it's going to survive throughout the life, throughout the mission.
So you got 30 MeV, but you test it at 42. Is that right?
Yes.
So that's you're guaranteeing the part performance per the data sheet at 30 MeV, but then 42 MeV is it's not going to fail. It's non-destructive, but you might go out of regulation. Is that right?
What we see is there'll probably be some larger transients. The transients will kind of increase as the energy increases. But the big thing that we wanted to do is make sure that it didn't fail. There's no latch up, no destructive event.
Right.
So, and so that was the reason for the higher testing versus characterization. Yeah. Most customers want to see how the part is going to perform, under a 30 MeV, which is a higher probability that they're going to see that level, that energy,
right,
of
course, and being the power system, if it does fail, it takes the whole system with it, right? So
yeah, it's we do have a little bit high pressure that if we're the first to fail, then the satellite is not going to operate. So it's always a challenge.
Okay, so where would VSC not be appropriate? Like we've gone through why you've picked it, why you've selected the specifications you have, and kind of why it's appropriate for new space applications. But like, it sounds great, but like, where is it not going to work?
So, I mean, every mission will have a different spot on the reliability versus cost curve. So the VSC is on the lower cost, portion of that. But VPT is, we've been developing parts for many, many years. We have extensive amount of successful missions for higher level screen parts. So, if you're looking, we kind of concentrate on the VSC around the 5-year type mission. But if you're looking for 10, 15-year type missions, the total amount of radiation is probably going to be on the low side. If you have a manned mission, where you're going to move more towards higher reliability, and cost isn't as big of a concern, you're probably going to lean away and move more to our hermetic hybrid type parts. So it's just VPT has an extensive range of products, and this is another addition to it. And we think it's going to be really applicable to this new space type market that are shorter missions, that are higher volume, that are lower cost, that are shorter development cycles. But if that isn't what you're looking for, we do have other products. So our SVR product line, that's our highest level of radiation, our highest level of screening. And that's a 100 kilorad part. That's an 85 MeV part, right? So that's for your 10 to 15 year type missions.
So if I'm going to the moon,
So that one is designed around the aerospace tour, right? For deratings, for component screening, things like that. We have the SVL series, which is 60 kilorads, 85 MeV. And that is in all of these higher level screen parts are hermetic hybrids or hermetic. And then we have the SV series, so that's 60 kilorads, 44 MeV. So it gives kind of a wide range of available products, and with that it's cost too.
Right.
So the higher level of screening, the higher level of radiation, our BOM costs go up, our screening costs go up, the part is more expensive. So what our goal is to have a large range, right? To make sure that we have a part that's offered for every application.
That's suitable for every application. Yeah. Okay, that makes sense. So thank you very much. I believe you're at an exhibition next week. Is that right?
Yes. So we're going to be in SmallSat in Amsterdam.
Mm-hmm.
Next week. We're going to be at booth 212.
Right.
So, please ask any questions through the Ask a Question box today. But if not, and you're going to be at the show, please stop by, ask in person. We'd love to talk to you and ask any additional questions that you have.
Okay. And then you're at RADX and Space Tech Expo later on this year.
Yep. Right? Somebody at VPT, somebody from VPT will be there. I don't believe that'll be me, but somebody will be there. So yeah, September, we have the end of September, beginning of October is RADX, and November is Space Tech Expo. So we'll be at both of those, and somebody will be available at all those to make sure that they can answer any kind of questions, or if you need help figuring out what level of product you need for your application, we're more than happy to help. So please reach out and let us know.
Thank you very much. So we've got a couple of extra slides that we've included in the presentation for the download. We're not going to go through them directly now, but we thought you might like to take a look at some of them. Thought they might be helpful, and hopefully they are. So thank you very much to everyone. A reminder to the audience, you can still submit your questions using the Ask a Question box. And we're now going to open up to the Q&A session. So just give you 1 second, and I apologize. I'm going to have to log back into my machine. Okay, so here's our first question. What sort of new space missions are good fit for VSC series?
So what we're concentrating on are unmanned applications that are looking around a 5-year life cycle. There are still a lot of military operations that even though they're in a low Earth orbit application, still they're concerned more about reliability of the part. So each system is going to be a little bit different. The VSC is targeting the lowest cost that you can have and still have a radiation kind of guarantee and screening. If cost is not as much of a concern and reliability is, you probably want to go with one of our higher level screen part to make sure that you have enough margin. So it really depends on what the mission is, what the system requirements are. And again, we're happy to help. Please reach out and we can help guide you if you do have any questions.
So short duration, low Earth orbit ComSat, great.
Yeah.
Geostationary orbit, maybe not.
Maybe not. Yeah.
Okay. Got a question here. Can you list some famous programs and vehicles that VPT parts have been used on? Also, can you share what kind of bicycle you're riding these days?
Oh,
I think this person knows you quite well.
For as far as famous missions, wow, we have thousands of missions that we've been on. I believe we've been to every planet, including Pluto, asteroids. So there's a lot. There's a lot of different missions. I don't know if I can single any couple out, but many different missions. A lot of histoy.
So you used to have a flight heritage page on the website. I'm not sure if that's carried through to the new one, but maybe they could look on there.
Yeah, that's a really great point. So yeah, I think there's definitely a section on the website that some of our bigger customers and flight heritage. That's a good point.
Yeah. So next question.
I'm going to bypass the bike one for now.
You sure?
Yeah.
You did. Okay. We might come back to that later.
Might come back to that later.
Can I learn what is test level for random vibration in GRMS?
Yes, we can provide all of that to you. I do not have it off the top of my head. For the VSC specific, it's different levels for hybrids and VSC, but yeah, we have we can definitely get all that.
Okay, so we'll go back directly with some more information later on.
Yeah.
Okay. Okay. Are the parts molded or lidded and filled?
Sure. It is an epoxy mold. Okay, so it's not it's not a structure that is filled. So yeah, it's a very rigid epoxy, designed for very rigid structure for shock and vibration requirements.
Okay. How did you define the minimum screening needed for ES Plus for this component? What is the reliability of ES Plus versus K?
Oh, that's a good one. So how we came up with ES Plus is really identifying every step in the process and where it is. So first of all, Class K is a hybrid spec. Okay, so some of the stuff doesn't apply at all. for obvious reasons. But if you look at it just from environmental type screening, temperature, vibration, things like that. What we try to do is identify what where we see failures, if we can associate each one with a cost, and how to pass any kind of savings on to the customer. So ES Plus is what we feel is a kind of a compromise to that. Right. So we're still offering burn-in, we're still offering temperature cycling, but we're doing it at a reduced rate to try to reduce lead time, to try to reduce costs. As far as reliability, right? I mean, the more screening that you have, it will be any kind of failures are going to be screened down. So there is a higher reliability with the Class K than it is for the ES Plus, but we were trying to meet a balance of cost and reliability. And let us know if you don't think that we've met that, because we are, we want to make sure that we're passing on the best part that we can to the customer.
I believe you've got some flight heritage on ES parts as well, kind of historically over time. So it's not something you've gone into cold. It's something you've seen it works.
Yes.
Yeah. In electrical point of view, specifications and components, is there any difference between ES Plus and qualified space versions? So I think that's conflating two issues slightly there.
Yeah. So, we are not picking a radiation hardened component to put in there.
Yeah.
To make sure that we're, we're very clear, this is not a radiation hardened component.
Yeah.
So there's going to be differences. There's going to be electrical differences that we have to design around from an individual component that we use.
Yeah.
Now, as far as if you look at our overall converter as a component, it will be similar electrical performance as our radiation hardened line. When we talk about regulation points and transients and things like that, it will be similar. The hybrid will be a little bit tighter on a lot of the tolerances, just because of the way it's built. But overall, overall converter point of view, it's pretty similar.
Okay. Do you contemplate, as part of the lot screening, radiation tests for SEE and TID for ensuring that potential modifications in the foundry process did not modify the radiation tolerance observed during qualification?
Yeah, so so that's the reason that we test total dose on a component level, is to look for those foundry changes. I mean, that's a really good point of view, really good question that we have to address. So, someone that is developing this part on their own, if the foundry changes, the radiation performance can change, and that's why we do the component level screening. So each lot of component that we put in, we look at a sample and make sure that the parts don't shift. And that's why we have, yearly screening on the overall converter to make sure that that hasn't shifted.
So as an additional on that same question, do you think for COTS, where there is no traceability of the foundry process, modifications between lots is necessary? Do you think for COTS, where there is no traceability of the foundry process modifications between lots, is it necessary this type of screening?
It kind of goes back to where we considered reliability versus cost. And that kind of ultimately what it comes down to. Would we like to know if the foundry changed? Yes, we would. And we, if they if the manufacturer releases a change notice, and we are made aware of it, then yes, we do go do additional testing to make sure. But a lot of times with COTS components, you don't have that information. And so that's why we have to do, as much work as we can to make sure that we're minimizing and mitigating those risks.
Right. Can you talk about the expected reliability of these devices? For example, what is the expected life for these devices? How did you decide 96 hours was sufficient burn-in to eliminate infant mortality? And have you tested these parts to failure to determine activation energy?
Wow, that was maybe a lot of questions.
Should we go with the first one first?
Yeah, let's maybe break that up a little.
Reliability of the device, firstly. So, kind of what's the expected reliability of this part? Can we justify it?
Yeah. So, with this, we do full, mill handbook 217 calculations that look at, mean time before failures. We do extensive life tests, qualification tests during the qualification process to try to determine length of reliability.
Right.
So when you ask, is 96-hour burn-in?
Yeah, so
burn-in specific.
Yeah, so what is the expected life for these devices? I believe that's the MTBF data is in the data sheets for each of the parts. And then how did you decide 96 hours was sufficient burn-in to eliminate infant mortality? That's a great question.
That's a great question. So what we did is we looked at all the history of burning in components. Where do we see failures? Okay. And where we saw really the highest failure rate is in like the first 24 hours.
Right.
So we knew that we needed some type of burn-in to screen that out. What is the right number? That's a good question. We did come up with 96. Should it be 96 or 48? These are good questions, and I'm not sure that we're right. We thought, looking at our data, we said that this is going to be the lowest reliability for the cost.
Yeah. So,
we could burn in more, and that's kind of feedback that we love to get.
Yeah.
For the cost.
Yeah.
And so we're navigating this along with many of the other customers, making sure that we're trying to get the right screening apart.
Right. And then the final one from that question was, have you tested these parts to failure to determine the activation energy?
So yes, so when we look at single event type testing, so when we look at failure rate for total dose, originally, when we went and developed the part, yes, we tested everything to failure. We don't test that on an annual or lot type basis. So we went to look sure when we were originally doing the development and figuring out what the capabilities of each component were, to figure out what kind of capabilities we could have, we did that type of testing. But we don't repeat that on any kind of annual or lot type basis.
Okay, next question. So for VSC, is there a subgroup that receives testing over a higher number of temperature cycles? I think the answer to that is no. They will go through the same.
Yes. So part of the cost reduction was to not have the different screen levels. To have standard parts so everything can move through the manufacturing process as seamless as possible, as quick as possible. So for our hybrids, we have a lot of different screening levels. That means, this order has to be screened at one part, the next order has to be screened at another part, which causes a lot of delays, in the manufacturing process. So only having one screening level streamlines that, and again, that all relates to cost savings and time.
But you're still open to have that conversation with customers.
Sure.
Obviously,
it depends on the situation, right?
Yeah.
If a customer requires DPA, I'm not sure quite what he's asking about that. It can add a lot of cost to the buying of a power supply versus me building my own. What info can you give me to reduce the perceived need for DPA?
So first of all, when we talk specifically about the VSC series, we can't do DPA.
Right.
Okay. So that is a hybrid question.
Yeah.
And that's really a requirement, that the systems engineers have, as far as making sure that the part is what it says. And so any kind of destructive part, of course, adds destructive testing adds a lot of cost because they have to end up throwing it away. But we do a lot of testing internal to make sure that that we are selling a high reliability part.
Okay. Sorry, we are getting quite a lot of questions here. Unfortunately, we're not going to be able to get through all of them, but we're going to try and go as quick as we can.
Well, I'm glad people are asking questions.
Yeah. So converters are closed loop systems. How does someone assess the performance of the converter in a system via analysis, apart from testing the final implementation? So we've got to test the whole circuit, right?
Yeah. They need to test their overall system. For stability. So unfortunately, we do not offer SPICE models. A lot of people ask for some kind of simulation model. DC to DC converter is a very complex part. And we develop SPICE models internal, but not really for they wouldn't be applicable for customer use.
Right.
So the best way is to get everybody's system is different. Everybody's load is different. Everybody's operating system, operating conditions are different. So the best way is to test the part out, in the system that's going to be operated, and to really ensure that they're getting this, the performance that they need.
Yeah. So this is a multi-part question here. So please describe how VPT decided VSC is a reliable product. What kind of testing and what sample sizes were used? And what are the results, e.g. fit rate, MTTF? What manufacturing controls does VPT have to avoid workmanship and manufacturing issues? What is the life guarantee on VSC at temperature extremes and LEO radiation? Does VPT provide derating guidelines for the VSC product? So I think we'll have to split that up because that's too many questions in one go. What kind of testing and sample sizes are used, I think, is the first.
Okay, so when we talk about individual component radiation testing, we pick 5 pieces from each lot.
Right.
And that's for radiation testing.
Okay, and then so next question was workmanship and manufacturing issues. How do we avoid them?
So we have very extensive internal procedures that that highlight and document the part through every part of the process.
Right.
And then that is and then we have travelers that follow it through to make sure everything is done. We have visual inspection at at several points to make sure that everything passes, and then we have overall inspections to make sure it's good. So all these are internal processes that we have for manufacturing, and all these stem from our high reliability line, right? We're building high reliability parts. We've been doing it for 30 years. Many successful missions. So it's the same. We're using the same manufacturing processes. It's different components, but our philosophy has not changed.
Right.
I think there was a derating question.
There is, yeah. So do you provide derating guidelines?
Yes, we have derating guidelines. Our derating guidelines for the VSC is an internal document, but yeah.
So that could be under NDA potentially shared.
Mhm.
Right. Okay. And then the last question was temperature extremes and radiation. So how do we guarantee the life under temperature extremes?
How to guarantee So, part of that during temperatures extremes, we do temperature cycling. If you're talking, and we do, during the qualification process, we run it at, maximum temperature for 1,000 hours, make sure that it's, still running. We do, extensive life type testing for the parts. So, that's kind of all part of our, qualification process.
Yeah. So a quick question here. Can you connect VSC modules in parallel and or series? Yes, you can. Yes, it's actually in the datasheet. And there's a guideline as well, isn't there? On the website.
So for parallel operation, we only allow the 100 watt to be paralleled. So, if anything below, you would just use the next size up converter.
Yeah.
But for parallel operation, it needs a share type connection, which our VSC 100 they have that. And now, when you say series, I like to call it stacked.
Yeah.
Okay. So you take 2 5-volt converters to make a 10-volt converter, and all of our isolated products can do that, but they have to be isolated in order to do that. So anything that's isolated, you can stack the outputs to create, different output voltage configurations.
Okay.
Probably one more question.
We've got time for one more question. Yeah, I think. Right. What about launch vehicles? Launch vehicles are, simply put, a mission that cannot fail, making reliability king. Is VSC the part applicable for these types of missions? Would you see an SVL or SVR series product as a better match for a critical launch application?
I think that, we're looking at like SVL type, SVL, SVR type series is more designed for that application. VSC is more driven for the cost sensitive components, cost sensitive designs, higher volume satellites, things like that.
Yeah.
So if reliability is your number one objective, you should choose the highest reliability part that we offer.
Okay, this one's too good. I've got to ask this one. Sorry. Do the VSC series regulators have monotonic voltage rise during turn-on transient?
Yes. So that's something all of our parts require. But yes, very good question. That can cause a lot of digital instability.
Okay, so that's it. Thank you very much, everyone. Any questions we haven't addressed, we'll reply back to you directly. I'm sorry we couldn't get to all of them. As a reminder, there's a survey that will pop up at the end of the program. 3 quick questions. If you can please answer that, we'd really appreciate it. You'll be emailed the link of the recording. And once again, thank you very much. We really appreciate you tuning in and listening in today.
Yeah, thanks, Don.
Thank you very much.